Alright, you guys, this video is going to be just talking through this example of a series question that you might get on your AP exam a couple years ago. And we've talked in class about how we only have so many new topics that they could dedicate an entire question to. So historically, you can count on probably having either a parametric or a polar, most often a parametric, and that's the kind of question that says there's a particle moving and it gives you two equations, an x and a y. And then we're going to have one that's probably dedicated to Maclaurin / Taylor series / power series, some sort of variety, and that's our current topic. So let's talk through this one. First of all, the function we're dealing with is the natural log of 1 plus x cubed. All right, so we're going to be probably dealing with some sort of series expansion of that function. And maybe dealing with polynomials, a certain amount of terms. And the first thing they tell us is the series for natural log of 1 plus x. That's not one of the main ones that you have to memorize, and for that reason they just give it to us. First question, use the series to write the first four non-zero terms and the general term for f. So what we need to do is use the function f, which is up above, and use this one that we have to get the first four non-zero in the general. So first things first, non-zero terms, that doesn't mean we're going to do a fourth degree. That means we need four terms. That might be out to the fourth degree, or it could be out to the third degree, or it could be any degree, fifth or sixth, if some of those terms happen to be zero. So your answer needs to have four terms that aren't zero. The general term is going to be kind of like the formula term, and we're doing that for f. So if we start with what natural log is equal to, natural log of 1 plus x, that's x minus x squared over 2. Notice it doesn't have the factorials in it. Those have been eliminated through the process of finding this polynomial. And then the general term, negative 1 to the n plus 1, that just makes it alternate, and it makes it start with a positive term, because the first term, the first degree term, would be negative 1 squared, which is positive. We just get x to the n over n. Nice and simple formula. What we want to do is use that formula to write the first four terms of f and the general term for f. And if you're going to start with what we have and end up with f, the only difference is the x cubed. So all we have to do here is replace our x's with x cubed. And this is worth 2 of the 9 points, and those 2 9 points should be basically automatic. The natural log of 1 plus x cubed is equal to x cubed minus, we put x cubed in and then square it, we get x to the 6th plus x to the 9th, because x cubed cubed, we multiply the two 3's together and get x to the 9th, so x to the 9th over 3 minus x to the 12th over 4, and there are my first four non-zero terms. The general term, the only thing that I'm changing is that I'm replacing x with x cubed. And you could write that as x to the 3n over n, but x cubed to the n is the same thing. So there's 2 points worth. That really didn't take much thought on my part. So we'll be grateful if we see that. Those are the first 2 points. And really remember, we're looking for about 4 to 5 average. So if you can get those two easily, you're well on your way. Okay, so let's see what's next. The radius of convergence of the Maclaurin series for f is 1. Determine the interval of convergence. When we used to do these, the first step, the step where you had to do the ratio test, that was to find the radius of convergence. That told us how far to the left and right of the center we had to go, and these are the x's that would make this series converge. Well, they're telling us that the radius is 1, and since we are a Maclaurin, that means we're centered at 0, we're going to get one of these, either negative 1 to 1 with round, or negative 1 to 1 with square, or one of each, one round, one square. But that's what we're looking for here, the interval of convergence. And if you recall back when we were doing these sections, once you got the radius, the only thing left to do is to check the endpoints. So what we need to do is take the series for f, which we found here in part A, plug in -1 and 1, and see whether they converge or whether they don't converge. So start on the left, and I'm going to try -1. At -1, if I plug that into x, I get -1 because -1 cubed is -1. The second term is also going to be negative because I have the negative sign, but then I do x to the 6th, and that turns to +1. So overall, I get a negative and a positive, gives me a -1/2. The next one was positive, but I have x to the 9th. So I get -1/3, -1/4, and so on. So this is a harmonic series, but it's all negative. Doesn't matter if the harmonic is negative or positive. A negative harmonic adds up to -infinity. And either way, this is divergent. All right, so we are not going to include -1 in the interval of convergence. X equals 1. This is going to be similar, but we're going to start with x cubed, and 1 cubed is 1. The second term is going to be minus because we have a negative sign, and then the term is just 1/2, and then this one's going to be the same but alternating. So this is the alternating harmonic. And remember, any series that the terms approach 0 and they also alternate plus minus, that's convergent. So what we knew was it was from -1 to 1. Now we know that the -1 is not included. The +1 is included. And here's our answer. That's the way they wrote it on the AP answer key. The way we might have done it in class was like this. I kind of like the way they did it because it's easier to tell. You know, some of your squared off brackets aren't so easy to distinguish from the rounded ones, but the less than or equal to, it's easier to tell the difference between that and just less than. So let's go with the way they did it. Plus, it's just the way they did it, and that's always a good model. All right, part C. We need the first 4 non-zero terms of the Maclaurin series for f prime of t squared. So we have a series for f. What needs to happen here is we need to take its derivative and plug in t squared. It's not bad. So let's leave f showing at the top. What we have here is a series for f of x. So f prime of x, no big deal. We're just going to take derivatives a term at a time. The derivative of x cubed is 3x squared. The derivative of x to the 6th over 2 is going to be, let's see, we bring the 6 down and we get 6 halves, which is 3, and then we decrease the 6 to a 5. So that's -3 x to the 5th. X to the 9th over 3, the 9 comes down and cancels with the 3 that's down there, and we get plus 3x to the 8th. And then x to the 12th over 4 is going to be -3x to the 11th. Okay, so there's the series, or there's the polynomial for f prime. The question was, what's f prime of t squared? Well, that's as simple as taking the x out and putting in a t squared. You put in a t squared, all you're going to do is change the x's to t's and then double all of the exponents. So 3x squared with t squared subbed in is 3t to the 4th minus 3t to the 10th plus 3t to the 16th minus 3t to the 22nd. So that part is f prime of t squared. Let's see what's next. Now we define a new function. All right, this is a classic example of one that looks crazy, but it's really not as bad as it should be. G is the integral from 0 to x of f prime of t squared. This is officially testing you out on your second fundamental theorem. But all that means is the integral of the derivative basically just cancels out and it brings you back to the function. But we plug x in instead of t. So since g in reality is just f with x plugged in for it, we're going to use that, just the first two terms, to approximate g of 1. So let's get back down here and see where we were. Okay, so g is the integral of f prime. All right, so the terms that we just found, that was a series for f prime of t squared. If g is defined as the integral of that, then we're going to take the 3t to the fourth and so on and integrate it. So g of x is, I started out thinking this was going to be just back to the original f, but look how it's defined. Since we already have f prime of t squared, we just need to integrate that and plug the x in. So we need to take what we just found, integrate it, and plug in x. So 3t to the fourth is going to become 3x to the fifth over 5. The x to the fifth over 5 is the fact that we're integrating t to the fourth. And the x is because it's in terms of x now and not t. The next term is going to be 3t to the 10th is going to become 3t to the 11th over 11. The next one will become 3t to the 17th over 17, and so on. We actually don't need that to answer this question. It's said to use the first two terms to approximate g of 1. So g of 1 is going to equal, I'll plug a 1 into this x to the fifth, I'm going to get 3 fifths minus 3 elevenths. If you get a common denominator of 55, this equals 18 55ths. All right, so that's part C. A little confusing there, but if you just take what you got, and these questions a lot of times will be based on what you did in the previous question. Take the f prime of t squared, which we just found, integrate it, plug in x, and then use the first two terms only to estimate g of 1. Okay, last part. We look at D. The Maclaurin series for G, evaluated at 1, is a convergent alternating series with individual terms that decrease in absolute value to 0. So this is an alternating series whose terms go to 0, which means it has to converge. Not only does that converge, but whatever our next term is the max error of our current term. So what we found in C, they're saying, is within 1/5 of the true value. So all we need to do is see that the next term is less than 1/5. So it's good that we had this written out, because my next term is within 3t to the 17th over 17, and when I plug in 1, I get 3/17. So basically, because 3/17 is less than 1/5, I know that 18 55ths is within 1/5 of the true answer. All right, 3/15 would be 1/5, so 3/17 is a little bit smaller than that. All right, so because it's an alternating series and it converges, whatever the next term is our max possible error. The way they showed that on the answer key, which is a little more proper, and just talking it out is not something you can do on your test. This is g of 1 minus 18 15ths. That's the actual value minus the prediction we made in part C. That has to be less than 3/17, which is less than 1/5. So that's more of a technical way to say it. All right, so this is one good one. It's not an easy one, but these Taylor ones usually aren't. Don't feel discouraged if you feel like you weren't going to get 9 on that. Just try to get the 4 or 5 each time, and then if you can get some other ones, that's just icing on top. All right, so I'll see you in class. Keep studying for that AP exam. It's an investment that'll pay off. Young out.